Okay, let's begin. We're going to start a new topic. It's 10.1. It's on, we're going to talk about parametric curves. And I guess I'll kind of do it in one with 10.2, their calculus. Okay, so let's talk about what these guys are. We're going to kind of segue from these guys into something I think is pretty cool, called polar coordinates, but let's get there one step at a time. So, we're just seeing curves. So curves is when we have an equation, but we're thinking of it as a graph in scalar form. So this means you have some function of x and y equals a constant. So for example, y equals x cubed, or x squared plus y squared equals 4. So we see these and we realize that these are curves. This is like a cubic equation that has its own picture. And this guy is a circle of radius 2 that also has its own picture. But this is just one way to represent these curves. It turns out we'd like another way. Sometimes it's convenient to have each variable represented by its own function. So, technically, you've seen this already a long time ago, even though you probably didn't realize that what was going on. And we've also seen it this semester actually, but you've seen it as early as algebra and trig back in high school, back when we decided to, okay, let's look at the coordinates of the circle and let's define a function that maps the x-coordinate and the y-coordinate, and we will think of the x-coordinate as cosine of some angle theta and the y-coordinate as sine of some angle theta and blah blah blah, and you literally built trigonometry from that one assumption, gave you an entire new branch of mathematics. We're doing the same thing here, but we're going to take that a little bit more generally. Basically, we're going to look at, if we have a curve, it's calc 2, so it'll only be in two variables, x and y, a dependent and independent variable. We want to be able to describe each variable in their own right as doing its own thing and put them together afterwards. And sometimes we'll be able to build a lot of things with this. And ultimately, by the time we get to 10.3, we're going to build a new way to look at the universe, other than the rectangular coordinate system. But ultimately, this is kind of what we want to do. We want to actually look at each variable itself as a function on its own. So we'd like to think of x as some function of another variable called t, and y as some function of another variable called t, i.e. x and y are described in terms of some other variable t. The variable here, now it doesn't have to be t, of course, it's a dummy variable. The variable t is called a parameter. And hence the set of equations x equals x of t, y equals y of t are called parametric equations. And these guys rise to what we'll call parametric curves when you sketch a set of parametric equations. Now sometimes you can sketch the x independently of the y, sometimes you will want to sketch them together, but ultimately this is a new way to look at the x and y coordinate on a graph, look at them as individual functions in their own right. So we have a function that tells the x what to do and a function that tells the y what to do. These equations that we would set up are called parametric equations. They give rise to the graphs called parametric curves. Now, the system, so if I have x equals some function of time, that's why t is usually used. It usually represents time, but not always. And why is that? And we're given some limits on the t. This means we are looking of a curve with initial point. So this is the starting point. Given by x evaluated at a, y evaluated at a, and terminal point, or final point, x evaluated at b, y evaluated at b. So that's just some notation. I want to introduce any other notation before moving on. Maybe let's do some examples at this point to kind of see what I'm talking about. Example. Sketch the parametric curve. Given by so let's say you have something like that, right? What does that actually give rise to? So one thing I want you to do is I want you to note this is a curve. We're going to see that it's in fact a straight line that begins at, when I plug in t equals 0, there's going to be 2 minus 0, comma 3 plus 0. And ends at, I plug in t equals 1, 2 minus 1, comma 3 plus 2 equals 1, comma 5. Now, we can look at this in a couple ways. One, not to do it this way. But it's worth showing you, I guess. As a table of values / coordinates, and we can plot points. So one way to think about a parametric curve, if you have no idea what it is you're looking at and you're trying to figure out what it's going to be, well, you can start with a table of values. You can take on various t values. T is like your independent variable here, and you want to know how your x and y will react to changes in t. So you can plug in a bunch of them. Like I said, we already know that 0 to 1 is going to be the full thing that we want. Let's make here like a half, a quarter, or 1/8. Here, 3/4, 5 or 8, whatever, random numbers that I'm plugging in. So the x is going to give us what actual coordinate here? So 2 minus 0, that would be 2. And the y would be 3 minus 0, that would be 3. We already found this here. X would be 2 minus 1, that would be 1. The y would be 3 plus 2, that would be 5. You can plug in a half. If your t is a half here, your x would be 1.5. Your y would be 4. If t is like a quarter, which is 0.25, your x would be, and your y would be 3.5. If you are at 3/4, so your t is like, I'm already getting bored with points. Like, yeah, I don't really like plotting points. But that's enough. Let's actually plot this. What this is saying is that 2, 3, 1.75, 3.5, 1.5, 4, and 1, 5 are all on the graph. So what we can do is we can go into the xy plane. And we can start to plot these points. They're all going to be on the right side, it looks like, so let's draw this in a different scale. So we will have two, and let's say there's a 5 here. Say that's 3 here. 3.5, 4. So 2 would go with 3. 3.5 would go with 1.75. 1.5 would go with 4. And 1 would go with 5. Anyway, as you can imagine, you can continue this process just by evaluating for different values of t, figure out what your x is doing, figure out what your y is doing. You'll be able to plot these coordinates and you would graph them. This one in particular is a straight line. But it doesn't go on forever. It stops at 1, 5. So this is actually the final point here. This is the terminal point. And it actually started here. So this is the initial point. So you can actually define a curve like that, but even more than that, which we're not going to get into this too much. This is more something you're going to get into in multi-2 probably. This is probably the first time you're going to see that. But not only we're defining a curve, we're technically also here defining a direction. So we're going to start down there and we're going to move up here. But ultimately it describes a line segment. The curve here describes a line segment. The parametric curve here is a line segment. Is a directed line segment. So it's a part of a line. Another way you could actually look at this, which is probably the better way, to take advantage of a pattern, or kind of think of these in the same breath, eliminate the parameter. So eliminating the parameter is in fact taking advantage of a pattern, as we'll see. So if my x was, what was my x? 2 minus t, and the y was 3 plus 2t. What we can do is, in this equation, I can actually solve for the t. My t is going to be 2 minus x. And what I can do is plug into the other equation. So now my y is going to be equal to 3 plus 2 times 2 minus x. The y is going to be 3 plus 4 minus 2x, or your y is going to be 7 minus 2x. And notice that here, this is now in what we call scalar form. And it's familiar, or it should be. So you do get that this does in fact lead to the equation of a line, but you are cutting off a certain section of it. So you can immediately just realize that, okay, this is going to be a line with slope -2 and y-intercept 7, but you actually only care about the part that moves from this point to this point, let's say. So this should be on that line. And you'd ignore the rest of it. So here you know that you would go from the point 2, 3 to the point 1, 5. So there are a couple ways you can look at it. You can actually just plot points, which we're pretty much never going to plot points, but it's just something to show you what is actually going on. But more than likely, we're going to want to take advantage of a pattern, and a very common technique to use is to try to eliminate the parameter, plug one function into the other, and get t's out of there. Now there are many cases in which we don't want to do that. We want to keep things in terms of t's because it's going to be easier to work with. But if you ever need to realize what this is in more familiar terms, this is an option. Now this shows up a common pattern. So if you look at the parametric functions, versus what the parametric curve would be. It turns out that if, say, x and y are linear, then the parametric curve will be linear. It turns out that if, say, your x is linear and your y is a quadratic, your parametric curve would be a parabola. And normally if one is linear and the other is a certain kind of function, your curve is going to be graphing the other kind of function on some kind of shifted basis. Now, if your x is a linear function of cosine, and your y is a linear function of sine, it turns out that this will give rise to a part of a circle or ellipse. These are very common patterns. So we can have straight lines, parabolas, pretty much anything else that's similar to that. If my x is linear and my y is quadratic, or my y is a cubic, then overall this is going to be a cubic. It's just going to be shifted, and etc. So let's look at a circle actually. So let's look at circles. These are very common. Suppose we have a circle x minus h all squared plus y minus k all squared equals r squared. How can we, there are many ways easily. So here's one thing you can do. We have x minus h squared plus y minus k squared equals r squared. We can divide our both sides by r. There's one. And now you can take advantage of the Pythagorean identity. We know that cosine squared plus sine squared is equal to 1. And so we will be able to say x minus h over r is equal to cosine, or in other words, my x is equal to r cosine theta plus h. And I'd be able to say my y minus k over r is equal to sine, or in other words, my y is equal to r sine theta plus k. And so this means one way to think of a circle is to think of this pair of equations. This is the parametric equations for the circle. Centered at h comma k with radius r. So there's another way to look at circles. It's a very common representation. When we do this, by the way, we have a name for it. So if you ever see this shows up, or I ask you to do this thing, now you know what I'm talking about. When we go from a scalar equation to a parametric equation, we say we've parametrized the curve You'd also do a lot of this stuff in physics too, I think, as well as electricity and magnetism. So if you happen to take those before you take multi-2, you see them before. I don't know. The order of these courses, sometimes they're messed up. There are a lot of things people do in physics and chemistry that until they've done like multi-2, they're not going to know really what was going on. But yeah, you can take a normal curve and you can split up the variables and you can write it in terms of some other variable. So for example, here I'm writing x and y as functions of theta. Here my r and my h are constants, by the way. R equals the radius and hk equals the center. So these are constants. So I can see a list of equations like this, and I know I would be looking at a circle. If both of them are linear, I know I'm looking at a straight line. If there's something else, then you kind of try to figure out what's going on. Pretty much never by plotting points, because if I give you something, or usually if your textbook gives you something, there'll be some pattern that you'll be able to take advantage of. In the same way that if you were given this as the beginning, you could have gone the other way by just subtracting h dividing by r, and subtracting k divided by r, squaring both and adding them together, you would get 1, and you can actually figure out that this was a circle. And if you're given a circle, you can go backwards and figure out that's that. And there's no unique way to do this, but this is one of the easiest ways to do it by taking advantage of the Pythagorean identity. Fyi. There's no unique way to parameterize. So pretty much anyone who's going to parameterize a circle, chances are they're going to do it this way. And so in pretty much any context where you see this, you're going to know, oh, I'm looking at a circle, but there's just, for some reason, they really need to split up the x and y separately and look at them separately, because it's going to matter for the whatever context it's working in. Okay. So, do I want to do an example of that? More examples. There's not much else I want to tell you about. I just want you to get used to actually thinking about curves this way. Unit circle. Is given by x equals cosine theta, y equals sine theta, where theta goes from 0 to 2 pi. It's literally how we created the unit circle. Notice that if I square each of those equations and add them together, I should get 1. So I would get x squared plus y squared equals 1. The equations x equals 2t plus 1, y equals t squared. That would give rise to a part of a parabola. which specific parabola is that? Well, one way you can do it is to, we have x equals 2t plus 1. This means that x minus 1 all over 2 is equal to t. This means I can plug that into y. This means that my y is going to be 1 over 4 x minus 1 squared. So that actually gives us a parabola. That's shifted so that when x equals 1, that will be at 0. So that doesn't go underneath the x-axis, so that makes sense. The y would always be 0 or bigger, and this part is going to be a quarter. So that's that parabola. Not much else to talk about at this point, I don't think. Okay. Let's actually jump into the calculus. The main takeaway is sometimes we want to be able to talk about our x and y as separate functions on their own, and there are many patterns that we can take advantage of if you're given in a parametric form that you can translate it to a more familiar form, and of course you can also go the other way. So I could have, for example, reparameterized this as setting x equals t, my y would be a quarter times t minus 1 raised to the second power. You can go either way. That is basics of what it is, how you actually figure out what something is, what you're looking at. Now let's actually talk about doing calculus with them. So let's say in some contexts it's very convenient for me to talk about the x and y as separate functions on their own. How do I go about finding a tangent line to a parametric curve, for example? So recall one formulation of the chain rule. One way that we can write the chain rule is to say that dy dx is equal to dy du times du dx. Now normally your u is thought of as an inside function, so you think of your y as a function of u, find the derivative with respect to u, that's like finding the derivative of the outside, multiplied by the du with respect to x, and that's multiplying by the derivative of the inside. Notice here, if we replace u with t and think of it as a parameter, we'd have dy dx. In other words, the slope of the tangent line to the curve y equals a function of x at the point x. We can think of that as dy dt times dt dx, but whenever your dt is non-zero, I can take its reciprocal and move it to the bottom. And so I would have dx dt. So that leads us to our first formula. So, if a parametric curve is given by x equals x of t and y equals y of t, we may compute the derivative dy dx by that equation. Whatever this function of t is, you're going to differentiate that guy with respect to t. Then whatever that function is, you're going to differentiate that guy with respect to t. So this is how we would find the first derivative of a parametric equation. Find the derivative of the y equation divided by the derivative of the x equation. And that's just taking advantage of the chain rule. One thing we would also know, if we wanted the second derivative, this is just d squared y dx squared, but we all know that we really think of that as just d dx of the dy dx. And we can pretty much think of this dy dx as the new function, right? So I can have d of dy dx over dx. So think of this as the new y, right? Think of this as the guy that is here. So basically what we're going to do is we're going to differentiate that function with respect to t and divide by the derivative of x with respect to t. So this is going to mean d dt of dy dx, which by the way, that's going to be a function of t if we use this formula, divided by dx dt. Another way you can actually get that by cheating is just to actually divide the top and bottom by dt, and you get it right away. That's one thing that's nice about the Leibniz notation for the derivative. It's actually pretty functional. You can kind of think of it as a fraction in many cases, which you'll use that to get away with a lot of things in differential equations and multi-2 and multi-1, and we're using it to get away with something here. So a couple ways to see that that's how we could find the second derivative. If x equals x of t and y equals y of t, define a parametric curve. Then we can find the second derivative of y with respect to x by taking the first derivative with respect to t of dy dt, where this guy is found via that, dy dx, where this guy is found via that formula, and divided by dx dt again. And so that's another formula. Both of these followed by the chain rule. Let's do some more definitions before we get into an example. Now recall, we obtain a horizontal tangent line. When dy dx equals 0. Of course, in parametric form, this would mean this means that your dy dt over dx dt equals 0. Of course, for a fraction to be 0, the numerator has to be 0. This means your dy dt must be equal to 0 for the tangent line to be 0, for the slope of the tangent line to be 0, and get a horizontal tangent line. And of course, because we're dividing by something, we want to make sure that we're not dividing by 0 itself. So, and dx dt not equals 0 at the same time. That's how we obtain a horizontal tangent line. We get a vertical tangent line, when the slope is undefined, but the curve at the same time is continuous. So, how can I make sure, where would that likely happen for the derivative to be undefined while the function is continuous? Well, potentially this will happen if the curve has no problem at the point that I'm considering. However, the rate of change of the x-coordinate is going to be 0, which means the function is not going to be moving to the left or to the right. It's going to be staying on the same x-coordinate. And so this happens when your dx dt equals 0, and your dy dt is not 0 at the same time. Now, you might be asking, what if they're both 0 at the same time? What if both dy dt and dx dt are approaching 0 as we approach a point? Then, to discuss what dy dt dx equals dy dt over dx dt, we can use ideas, locals. So in the case that your dy dt over dx dt is approaching 0 over 0, this is indeterminate. We can make sense of this using L'Hopital's, because that's actually one of the form where L'Hopital's works, assuming the function itself is continuous. So if it might go to 0, in which case it's a weird place, but it's horizontal, or it might become undefined, in which case that would mean it's like a sharp corner or something like that, or it will give you some other number, in which case it's just some other slope. So you can't really tell right away what's going to happen, so you just use L'Hopital's rule, take a limit and approach the point very carefully and see what's happening if both are approaching 0 at the same time. So we know how to find the first derivative and the second derivative of a parametric curve, and we also know how to talk about whether the slope of a tangent line would be horizontal or vertical there. And this is just also that we can examine the function and learn more about it. Do I have an example? Let's do an example. Curve is given by x equals t squared minus t plus 2, y equals t cubed minus 3t. No restriction given on the t, so you can assume your t's are going expanding throughout the largest possible interval. Since these are both polynomials, you can assume that your t will hit all values from negative infinity to infinity. A. Find the first derivative. Find dy dx for this curve. B. Find the second derivative for this curve. C. Find the points where the tangent line is 1 horizontal, 2 vertical. D. When is the slope 3? E. Find the equation of the tangent line. When t equals minus 2. So as written, you can realize that this function, if you were to write it in the other form, in the usual xy form, it would actually be, there are no ugly functions, but it would be an ugly function, right? I mean, you try to solve for the t here, probably the only way you're going to be able to do that is using the quadratic formula. You're going to have like radicals all over the place, then you're going to go and you're going to plug that in here, you're going to cube it, subtract t times 3 times that thing, so you're going to get y equals this really messy thing to the 3/2 power, well, it's going to be something plus something to a half power within a cube that you can expand. It's going to be messy. It's going to be messy to actually deal with this as a scalar function. But let's see if we can, without going back to the scalar function, actually compute all this stuff. Okay, A. How would I find dy dx?
dy dt over dx dt.
So first, let's find dy dt. What's dy dt?
3t squared minus 3.
And find dx dt? Huh? 2t minus 1. This means that your dy dx is going to be, you can take this divided by that, 3t squared minus 3 divided by 2t minus 1. That is going to be your first derivative. Of course, it's in terms of t. E. But I wanted to find the second derivative. Well, going directly by the formula, the second derivative is going to be the first derivative with respect to t of dy dx divided by dx dt. This is going to be the first derivative of, well, we just found that guy, 3t squared minus 3 over 2t minus 1. All of that's going to be divided by the derivative with respect of x with respect to t, 2t minus 1. So now we would actually find that using the quotient rule, I guess. So it's going to be the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. And then I divide by the 2t minus 1 again, so that's going to be the bottom cubed. this is going to be. Maybe let's clean this up a little bit, if it can be cleaned up. 12t squared minus 6t minus 6t squared plus 6. And I don't think that actually. Well, we have the 12t squared minus the 6t squared, so that would just give us 6t squared. So t is a common term, 6 is a common term, I'd be able to factor that out. So that'll be t squared. It's minus 6t, so it's just minus t. And plus 6 is plus 1. Over 2t minus 1 cubed. Any questions so far with these? Has anyone seen parametric equations before? Like something you've seen before? In math class?
Yeah.
Which math class?
High school.
High school?
Calc, BC Calc.
Okay, alright, cool. Anything confusing about parametric equations so far? 'Cause I mean, sort of glossing over things here, but at the end of the day, it's not really anything more complicated than, oh, just describe x and y as their own thing. What would that mean for the math that we were doing? It will mean these formulas end up being true, and we'll just kind of compute it. Now, you're really going to see uses for this guy in like multi-1 and multi-2, but I'm actually going to show you something that's going to be very convenient that we're going to learn here, and we're also going to continue to use it in multi-1 and multi-2, but let's continue with this problem. So that's how we found the first derivative and the second derivative. C. Where's the tangent line horizontal? So horizontal tangent line. So basically we want dy dt equals 0, but dx dt not. So dy dt equals 0 means 3t squared minus 3 equals 0. This means that your t is equal to plus or minus 1. But don't highlight that yet. Let's actually check. So check where dx dt equals 0. This means 2t minus 1 equals 0. This implies t equals 1/2. So, therefore, there's no overlap with that guy. Because dy dt is going to be 0 at plus or minus 1. Our dx dt is equal to 0 at 1/2. We don't have anything coinciding here. So, we have a horizontal tangent line. At t equals 1, t equals minus 1, or more specifically, because what does it mean to say that there's a horizontal tangent line at t equals 1 and minus 1? Well, that means if I plug in 1 for t in this guy, so that's going to be 1 minus 1 plus 2, that's going to be 2. And plug in 1 for t in this guy, that's going to be 1 minus 3, that's minus 2. At the point 2 comma minus 2 in terms of the xy coordinate system. There will be a horizontal tangent line at that point on the graph, as well as if I plug in minus 1, this ends up being 1 plus 1 plus 2. So that'll be x is 4, and if I plug in minus 1, this is going to be minus 1 plus 3, positive 2. So at those two coordinates, this curve will actually level out. It will have a horizontal tangent line. I don't know if there are max or min yet, so I shouldn't have done that, but I know that the tangent line is going to be 0 at those two coordinates. Of course, the vertical, C2, vertical tangent. So this means we want the x dt equals 0 and dy dt not equals 0 and curve defined, let's say continuous. Now this will clearly be continuous because each coordinate is behaving like polynomials, so each coordinate will always exist and be continuous, so the whole curve is continuous. So we have these guys, coordinates given by polynomials. So we'll have continuity everywhere. We don't even have to worry about that situation. So where would there be a vertical? Well, it's wherever the dx dt equals 0, but the dy dt not equals 0 at the same time. We actually found all the coordinates where these two things happen. Dx dt equals 0 at a half. Dy dt is not equal to 0 at t equals a half. So this means we have a vertical tangent at t equals 1/2. Specifically, I should say more specifically, just to, it's pretty specific. Specifically, at the xy coordinate equal 2, I would go here and I would plug in a half. It's going to be messy. Okay, so that's going to be a quarter minus a half. It's minus a quarter plus 2. What is that, 7/4? And if I plug in a half here, that's going to be 1/8 minus 3/2. 3/2 is 12/8. So it's 1/8 minus 12/8 minus 11/8. So at that coordinate, we'll have a vertical tangent line. Whatever this graph looks like, I don't know. Okay. How would you find when the slope is 3? Yeah?
You'd have to do 3t squared minus like dy d over dx equals 3 and solve for t.
1 dy dx, should be dx, equals 3. Now dy dx is just dy dt, 3t squared minus 3 over dx dt, 2t minus 1 equals 3. So this means that 3t squared minus 3 equals 6t minus 3. This means that 3t squared minus 6t equals 0. And this means I could factor this. So t equals 0 or t equals 2 is where the slope will actually be 3. So we'll have this curve will be increasing at a rate of 3 at the points where t equals 0 and t equals 2. Or more specifically, at 2, 0, and if I plug in 2 there, that's going to be 4, plug in 2 there, that's going to be 8 minus 6, that is 2. We had another point that was 4 comma something here, right? What was that?
Maybe it was 4-2 as well.
It was also 4, 2?
Yeah. Those are in part C.
What coordinate were we plugging in? T equals minus 1?
Yeah, I
And that gave us 4, and
4,
then,
think.
no, it was 4 minus 2, right?
Mm-hmm.
It was 4, 2?
Yeah, I wrote 2. I don't know why.
Yeah, I have 4 too.
Okay. Now that's, is that strange? Well, we'll see. What do you think that actually means?
It crosses over the same point.
It crosses over the same point twice, right? So the curve that we're doing is actually not a function. It's literally going to go at some point and come back to a point. So it'll pass through this point at some point, t equals
Is when the horizontal.
-1, and then it's going to do whatever it wants and pass through that point again when t equals 2. And that kind of shows you why there's like going to be a vertical tangent line at some point. Whatever this graph looks like, I don't know. I know something like that's going to happen. So this parametric curve here doesn't even describe a function. However, individually the components themselves describe functions that I can talk about. So that's actually pretty nice. Okay, so that is where the slope will actually be 3. Let's look at okay, so how would I find the equation of the tangent line when t equals 2? Minus 2. Bring it back to Calc 1.
It's like in t equals -2 for dy dx.
Okay, so first, we need 2 things to find the equation of the tangent line. We need m, which here we know that's going to be dy dx, evaluated when t equals -2. And we need a point, x1 comma y1, which is just going to be pretty much x of t comma y of t, again evaluated when t equals -2. So our m here is going to be dy dx at t equals -2, which is going to be 3t squared minus 3 all over 2t minus 1, evaluated at t equals -2. If I plug in -2 here, that's going to be 12 minus 3. It's going to be 9. Plug in -2 here, that's going to be -4 minus 1. So it's -5, so it's -9/5. And x1 comma y1 is going to be equal to, I'm going to plug in -2 for t in the x. It's going to be -2 squared minus -2 plus 2. Comma, -2 cubed minus 3 times -2. That's going to be 4 plus 4. That's going to be 8, comma. It's going to be -8 plus 6 minus 2. So that's the point. So now I can actually find the tangent line. This is the continued tangent line is y minus y1 equals n x minus x1. That's about it. One other application here. Is this the last thing that we're going to wrap up with in this section? Yeah, this is actually the last thing in 10.2. They talk about arc length. Now we found arc length earlier. Now we're going to find arc length for parametric curves. So, suppose x equals x of t, y equals y of t are continuous differentiable on some interval AB. My AB is the xy coordinate here. No, the t coordinate. So this is my my t is in AB. Then by the mean value theorem, we're going to use the same theorem that we used to prove the other one. We know that the change in x is going to be thought of as the derivative times the change in t and the change in y is going to be thought of as the derivative times the change in t. At some point in the interval tn minus 1, tn. So here's the picture. In case you're wondering what the hell am I talking about, well, you're probably always wondering what the hell am I talking about. What the hell is Jhevon talking about? It's like every class. So we have some curve going on, doing its thing, and in particular this curve can do whatever it wants. It doesn't have to obey the vertical line test or any of that stuff, right? Because when it comes to parametric equations, we just don't even care. But what we're going to do is, again, because the dissecting it in terms of the x-axis or the y-axis is not going to be of concern, because I'm not thinking of things in terms of x and y. I'm thinking of things in terms of some other t. So there's some other universe there with another invisible axis that we're not seeing on this picture that's measuring the t's, and it's pretty much connecting lines in this universe along this curve. Right? So this is where I start out with the t0, and I get the x of t0 comma y of t0. Then here I have the t1, so I get the x of t1, y of t1, etc. And all these coordinates are measured in terms of t. So now if I look at x as a function of t, mean value theorem will apply because it's differentiable, so I can get that. And separately I look at y as a function of t, mean value theorem will apply to that function. And so ultimately what I get is that the change in x, so I'm looking at some particular interval. On this interval, that's going to be true, and that will be true for each of these different segments, each of these different intervals. So my change in x at some particular point is going to be equal to the derivative at that particular point times the change in t, and the change in y at some particular point is going to be equal to the derivative of y at that particular point times some change in t. And so here's what we have. We have that the length of the line segment from tn minus 1 to tn is going to be using the distance formula. So that's going to be the change in x squared plus the change in y squared. This is going to be the square root of x prime of t at some specific point plus the y prime of t at some specific point. Each of those guys squared. The delta t, I can factor that outside the radical. and inside I'd be left with x prime of t at that point squared plus y prime of t at that point squared. So I end up with each line segment, and I'm really doing a lot of hand waving here, not really being too specific. Just want you to have the idea, you won't need to know the proof. That's going to be your delta t. We're just thinking of it as some positive distance. So we're assuming that the Tn is always larger than Tn minus 1. And ultimately, summing these in a Riemann sum gives the fact that the entire length of the curve on the entire interval AB is going to be given by summing all these guys on the interval AB of the radical of x prime of t squared plus y prime of t squared t. E. If a curve is given by x equals x of t, y equals y of t for t moving between a and b, where x of t, y of t are continuously differentiable, so they're continuous and they're differentiable and their derivatives are continuous. And the curve is traversed once as t increases from A to B, then the length of the curve on this interval is given by this formula. So, yet another thing we should have memorized, this actual formula. X prime of t, you're going to take the derivative, you're going to square it. Y prime of t, you're going to take that derivative, you're going to square that. And t. That gives you the length of the curve. And we're not going to do this, but you can try it on your own. Find the length. We'll probably just do this at the beginning of next class. Find the length of this curve on the interval, the t interval 0 to 3. And this at the end of this example, this will end 10.2. So next time we'll finish this up and we will start 10.3. So that's pretty much all I need to know for 10.1 and 10.2. 10.3 is the more existing one. Also, I have your test to give back because not everyone picked them. So let me also do that.